So this is 3-3, the beta lesson, okay? And yesterday we talked about this, and there's a picture on page 118 of your book of this graph, which is fourth degree. And we're contrasting this with example 2, which was meant to be done without a calculator. But the work here is not difficult. In order to apply the power rule, this fourth degree parent graph, it's differentiated to a third degree. Here's the picture that's in your book, in the margin on page 118. Here's a picture of the derivative, which isn't in your book. Let's see if this makes sense to you. Ready? This is like the big derivative puzzle where I slid this picture underneath that one. This is fourth degree. How many zeros does it have? 4. How many of them are real? 4 or 2 or none. But we can count these and see 4 real zeros. Now, if we were to move this graph up by just sliding it up, we could see that those zeros would become non-real, 2 at a time as we slid this up. Here's the derivative. It's third degree. It has 3 zeros. How many are real? 3 or 1. But we can see that all 3 are real. So now we're going to use the technology to do this problem as opposed to example 2, which was meant to be a non-calculator problem. So I'm going to go to the derivative. And I'm going to go second trace 0, which you did as far back as algebra 2. And what happened is when you do that, I got this value, which is a, when I trace this is the x value when the height is 0. So this value is in x until you move the cursor. So I went second quit on the calculator, and I typed x, whatever's in there now, store above the on key, alpha A. X store alpha A. And what happened was that whole value, I didn't have, that way I don't have to round it, because if you round during the problem, you're going to compromise your answer. And then I just did the same thing for this point and that point. They're the values along the x-axis. So I went to y equal y1 and said, put these inputs in for y1. And these inputs, A, B, and C, are the values where the derivative is equal to 0. The parent graph's in y1. So that's giving me the ordered pair on the parent graph, which then, I'll just take the one value. Ready? Just take A. Negative 1.862, rounded to 3 places. When that value gets put into the parent graph, you get negative 5.321. And the value of the derivative there is 0. That's what these points have in common. So if I go back up here, that T-chart gives you the value of the parent graph, where the derivative was 0, where the graph stopped falling and started to rise, where the graph stopped rising and started to fall, where the graph stopped falling and started to rise. But the important use of the technology here is storing these values, because then when you say y1 of A, all of that goes in the input in the function. If you round it before you put the input in, you're going to have a rounding issue, a rounding error in your answer. Okay? So this is just a calculator exercise. We're going to pause this, and you're going to use this example to do exercise number 11. Okay, so for problem number 11, got to be careful now. 11 is not written in standard form. So this is fifth degree. How many zeros does it have? 5. How many are real? 5 or 3 or 1. So I look at this picture and I say 3. No, it's 5. This is a multiplicity of roots. Okay, so this would be 1, 2, and the one at the origin counts 3 times, which you can tell by the behavior of the graph, because the graph behaves like y cubed. So the derivative is going to be 1 degree less. It's 4th degree. So it has 4 zeros. How many of them are real? 4 or 2 or none. But the picture looks like it's 3. Yeah, because this one at the origin counts twice, because you see the behavior as if it's a quadratic. So that's a double root. So what does this mean? Well, these values were integer values, so it's easier than the example. The derivative is crossing the x-axis at -1, 0, and 1. -1, 0, and 1 make y2, the derivative 0. What is that telling you? Well, at -1, the parent graph stops decreasing and starts increasing. At 0, there was no change in behavior. It was increasing through 0. At +1, it stopped increasing and began to decrease. So what you'll learn about the middle point is when the derivative is 0 or fails to exist, then you have a critical point. And if you have a critical point, you may have a max or min. You may have a max or min, but it's not guaranteed. So you see at this point it isn't. All right. Now we're going to go to the product rule. Now if I go back to the book, ready? On page 117, the sum and difference rules. What does it say? The derivative of a sum equals the sum of the derivatives. Okay. So if you add 2 functions, so I'm going to go over here and show you what this means. If I go to y equals, and I just make something up that's user-friendly. I'm going to add these. Ready? I'm going to add y2 and y3. What do I have? X squared and 2x. So the derivative of x squared is 2x, and the derivative of 2x is 2. Understand we're getting this? Just made this up. It's made up user-friendly number. So x squared differentiates to 2x. 2x differentiates to 2. So I want to do the sum. I want to do the derivative of the sum. So I think the derivative of y1 is 2x plus 2. I turn on y6, go to the table, and the table agrees. Okay, that's what's on the book. That's what's in your book on page 117. But if I change this to a product, then what would I get? Well, x squared times 2x would be 2x to the third. 2x to the third, the derivative would be 6x. Doesn't work. Doesn't agree. So what we're telling you is that what's on page 117 that applies to sums does not apply to products. And the product rule is here on page 119. Okay? Now, let's look at this right here. Right underneath where it says the proof of Rule 5. So in the way we did it, I said U was x squared, and V was 2x. So this is the difference quotient that you did in chapter 2. The top is the difference of the outputs subtracting up. In the bottom, that's x plus h subtract x. It really would be easier for you to read this if they would write that in that first line, so you know where this is coming from. Here's the derivation. We're not going to go through the whole derivation. We're just going to go through this part. What I drew a box around. Can you recognize what I drew a box around, which is what? They took this and inserted it in that line. They inserted that value in the box. By looking at that, can you tell what that is? No pressure, but one of my advisees saw it this morning. It's 0. It's negative u of x plus h times v of x plus a positive. They add to 0. It's an algebraic trick. They just introduced 0 in the middle of this so they could go here. So in order to make this a little more understandable and less cluttered, I just called these different terms, A, B, and C, and D. So here's what they're trying to do. But this 0 in the middle was in effect negative AD plus a positive AD. And that allowed them to go down here and group these terms. You don't have to follow the derivation. You should just be aware that they had this algebraic manipulation in here by adding a 0 that allowed them to go from the top line to the third line. And it's important you understand this. Ready? The derivative with respect to x of this product does not equal the product of the derivatives. So you're doing a exit ticket on College Board today, and I don't remember the specific question, but I'm telling you right now, if it's about the product rule, choice A would look like this. And the people that don't read all 4 choices are going to just leap to that choice, which is wrong. So let's look at example 4. Example 4 is on page 120 in your book. And they give you this. The product of these 2 binomials. And you want the derivative of this product. So you could expand this. You could literally build a lattice, and you could do this. This is an option. For this problem, it's not something you want to expect to be able to do. But for this problem, you have x squared plus 1. If you did this, x squared plus 1, and you multiplied it by x cubed plus 3, you would get x to the 5th, x to the 3rd, 3x squared plus 3. So your expansion would be y equals x to the 5th plus x to the 3rd plus 3x squared plus 3. And the derivative, y prime, by the power rule would be 5x to the 4th plus 3x squared plus 6x plus 0. Yeah, okay, that makes sense. That's what I've been doing. Correct. Except this, you have to understand, is meant to be a user-friendly problem to get you on board with what's going on here. If you had a trig derivative as one of the factors, you couldn't do that. So this is basically meant to be a training wheels problem to help you understand it. See, this answer down here will simplify to what we just got on the whiteboard. But here's how we do the problem, in this case, which would be the long way. U is the first term. The derivative of that would be 2x plus 0. The second factor is v. The derivative of that would be 3x squared plus 0. The product rule says take the first term, u, multiply it by the derivative of the second term, 3x squared. Then add the second factor, plus the second factor times the derivative of the first term. And when you expand that, that will take you back to if you had expanded the original pair of factors and then use the power rule on that. Okay? So I'm going to leave it up there. That's your model, and you're going to problem number 13, please. All right, so we're going to go over this. Ready? What happened? And again, this problem was built to work out. So you have, this is the first factor, this is the second factor. So I call x plus 1 u. The derivative of that would be 1. I call x squared plus 1 v. The derivative of that would be 2x. So the derivative of the product would be the first term times the derivative of the second term, plus the second term times the derivative of the first term, which would multiply, combine your like terms, and it would give you this, quadratic, because the original parent graph is a cubic. But if I FOILed this, I'd be here, and I could differentiate that right down here. They match. It's the same thing. But you need to do this, and somebody chatted that question. Why would I need to do this? Well, for example, which we didn't do yet, if this term were cosine x, it was a trig function times this wouldn't work. So you're getting the, we didn't get to the derivatives of the trig functions yet. They are in 3, 5.